Today's lesson is on parallel and perpendicular lines, and we have 5 objectives for the lesson. By the end of the class, after watching this video, you will be able to define parallel lines, to define perpendicular lines, and to define skew lines. You'll also be able to use the slopes of parallel lines to solve problems, and to use the slopes of perpendicular lines to also solve problems. So let's start with our first objective, which is to define parallel lines. Okay? Parallel lines are coplanar lines that do not intersect. Coplanar means they are in the same plane. So two lines drawn on a piece of paper, the piece of paper is the plane. If you drew them on a whiteboard, the whiteboard would be the plane. But they need to be two lines that are in the same plane that do not intersect. And for example, right there, line L and line M are parallel. If I continue drawing them forever and ever, you can see the arrows on both the left and the right of both those lines going in both directions show that these lines go on and on forever and ever in both directions, and yet they never touch. They always stay the same distance apart because they are parallel. And I can show they're parallel by putting these little arrowheads on it, and that is the notation that shows me that these lines are parallel. And if I have multiple sets of lines, for example, if I add these lines, line AB and line CD, obviously lines L and M aren't parallel to lines AB and CD, because if I continue to draw them out to the right, they would intersect them. But if I want to show that line AB is parallel to line CD, I can do that by putting arrowheads on it, but it can't be the single arrowheads because then that would be showing that they're parallel to L and M as well. So by using these double arrowheads, I'm showing that L is parallel to M and AB is parallel to CD. And the notation we use to show that is this double straight vertical line, which reads line L is parallel to line M, and the other one reads line AB is parallel to line CD. And we talk about parallel lines because they're important. They are everywhere in the real world. So for example, hardwood floors, right? The hardwood floors, if I keep drawing those lines all the way to the end of the wall in the room, they never touch. These are parallel lines. Another example of parallel lines is parking spaces. Right? If the lines weren't parallel and cars were going in a non-parallel way, then when they came out or went in, they might hit each other. And so the lines in parking spaces are parallel. Another example of parallel in parking is parallel parking. In this drawing over here, the green car wants to park in between the yellow and the black car, or excuse me, see the yellow and the red car. So the green car goes past the space and then is going to back in. I'm sure we've all done that. And it's called parallel parking because when it's done, the side of the green car will be parallel to the pavement. And speaking of parallel parking is one of those things where if you do it alone, it's no problem. You can back right in. When you try to do it when people are watching or somebody else is in the car, all of a sudden you act like you've never parallel parked before. Okay. Finally, perhaps the best example of both parallel and perpendicular lines are maps. So for example, most of Oakland is built on a grid that is some streets go north-south, some streets go east-west, and Oakland Military has two parallel streets, Market Street and Lusk Street, that are on either side of it. And if you blew out this map and continued on, you would see that Market Street and Lusk Street never touch because they are parallel lines. Okay, so in our notes, we can write down the definition of parallel lines, which is coplanar lines that do not intersect. And the symbol and the notation that we're going to write down is those double vertical lines. That's parallel. So in this drawing here, we have that line AB is parallel to line CD. And note the matching arrowheads on line AB and CD that show that these lines are parallel. Okay, we said we had 5 objectives. We just did the first one of defining parallel lines. So now we're going to do the second one to define perpendicular lines. Okay? And perpendicular lines are lines that intersect to form a right angle. So for example, line G and line H there, they intersect and they form a right angle. That's what that right angle sign, that right angle sign means, is that's a right angle, a 90-degree angle. And so we would say that line G is perpendicular to line H. The notation we use is an upside down capital T, and so we would just read this as line G is perpendicular to line H. And a key fact to remember when you do this is that when I create that right angle with line G and line H that are perpendicular lines, I'm not just creating one right angle. In reality, I'm creating 4 right angles. All the angles that are made by the intersection of G and H are 90-degree right angles. And like parallel lines, perpendicular lines are all around us. So I thought a really good example was railroad tracks and railroad ties. The railroad tracks are parallel lines to each other. They have to be. They have to be equidistant apart, otherwise the train will derail. And then the railroad ties are perpendicular to each other. They hold the railroad tracks together. But at any intersection of the railroad tie and the railroad tracks, those make right angles. So any railroad tie and any railroad track together are perpendicular lines. Another good example of perpendicular lines are window panes. That in this picture over here, you can see there are vertical lines that hold the windows together, vertical pieces of wood and horizontal pieces of wood, and they meet at right angles. So any of those windows are right angled windows, and so the window panes themselves, the vertical and horizontal lines are perpendicular. And just like the map was a really good example of parallel lines, it's also a really good example of perpendicular lines. Again, looking at our map of Oakland Military, the 39th Street and Lusk Street, they meet, and they meet at a right angle. So they are perpendicular. So again, most cities, not all, but most cities are built on a grid. And so most streets in cities are either parallel, they go on and on next to each other and don't ever intersect, or they are perpendicular, that when they do intersect, they intersect at right angles. Okay, we said that we want to define our perpendicular line as a objective. So let's do that. Lines that intersect to form right angles, and using the symbol and notation, the symbol for perpendicular is that upside down capital T, and we'd read this as line G is perpendicular to line H. And note that we know that because of the right angle sign in the perpendicular line diagram there. Okay, we said we had 5 objectives. We've now done 2 of defining parallel lines and perpendicular lines. Our third objective is to define skew lines. So that if lines don't intersect, there are 2 possibilities. They're either parallel or skew. So parallel lines lie on the same plane and don't intersect. That's what we just said. So for example, that red line and that blue line, or in this one, line L and line M are both in plane P. Those are parallel lines. They go on and on forever and don't touch and they're in the same plane, so they are parallel. However, skew lines are in different planes and do not intersect. So it's tough to draw on a computer screen, but I'll do my best here. So you can see that there's a plane, think of it kind of like a piece of paper that has line AB in it. And then I took a pencil and sort of shoved it through the paper at point C so that line CD is also showing there. And you can see that line AB and CD, if I extend them out forever and ever and ever, are never going to touch, but they are still, but they're not parallel lines because they're not in the same plane. So those are skew lines. So AB does not intersect with CD, and since they're not in the same plane, they are skew lines. And then finally, for parallel, perpendicular, and skew lines, that if segments or rays are parallel or skew, if the lines on which they lie are parallel or skew. So in that diagram, you can see AB is a line segment. It's not actually a line, but if I pretended it was a line, the line that it runs that contains AB in it still wouldn't touch BC or CD because they are skew. So let's go to our notes and write this all down, that skew lines are non-coplanar lines that do not intersect. And in this diagram, you can see that AB does not intersect CD. And since the lines are not in the same plane, they are skew lines. Okay, we said we had 5 objectives for the day. We've now done the first 3 of defining parallel, perpendicular, and skew lines. The next 2 objectives involved parallel and perpendicular lines and the slopes of them used to solve problems. So to do that, to do our 4th objective, we're going to have to first define the slopes of parallel lines, and to do our 5th objective, we'll have to define the slopes of perpendicular lines. So let's do that. So the slopes of parallel lines, if 2 lines are parallel, then their slopes are equal. And the converse of that is also true, so that if 2 lines have equal slopes, then they are parallel lines. For the slopes of perpendicular lines, if 2 lines are perpendicular, then their slopes are opposite reciprocals. And the converse of that is also true. If 2 lines have slopes that are opposite reciprocals, then they are perpendicular lines. And opposite reciprocals are 2 numbers that are opposites, which meaning that they have opposite signs. So one is positive and one is negative, and they are reciprocals. So if you take the numerator and denominator and flip them around, those are reciprocal lines. So for example, the opposite reciprocal of A over B is negative B over A. One of them's positive and one of them's negative, and they are reciprocals. A over B, with A as the numerator and B as the denominator, is the reciprocal of B over A, with B as the numerator and A as the denominator. So some examples of opposite reciprocals, and you don't need to have this in your notes, I just wanted to show you so you really understand what opposite reciprocals are. Negative 4/5 and 5/4. One's a negative, one's a positive, and I just took the 4/5 and flipped it around. 1/2 and negative 2. 1/2 when I flip the numerator to the denominator becomes 2 over 1, which of course just becomes 2, and I make it negative for negative 2. 3/7 and negative 7/3. Those are opposite reciprocals. And the final example I have is 5 and negative 1/5. Right? 5, if I make it into a fraction, is just 5 over 1. And so if I flip it around and make the numerator the denominator and the denominator the numerator, it becomes 1/5, and it's positive 5, so it would be negative 1/5 to make it the opposite reciprocal. A second thing about opposite reciprocals, just to make sure you understand it and you can determine if 2 numbers are opposite reciprocals, are if I multiply them together, if I multiply any 2 opposite reciprocals together, the product is always negative 1. So for example, going through those examples we had, negative 4/5 times 5/4 is negative 1. 1/2 times negative 2 is negative 1. 3/7 times negative 7/3 is negative 1, and 5 times negative 1/5 is negative 1. Okay, so we said our objective was to be able to do some problems with the slopes of parallel lines, and example 2 over on the left there is just such a problem. It's asking us, are these lines parallel? Well, just glancing at it, it sure looks like they are, right? They look kind of like railroad tracks. They never touch on this graph. Maybe if I continue them out way at the bottom or way at the top, eventually they would, but it's tough to tell. They look pretty parallel. But the way to check for sure is go to my definition, that I know that if 2 lines are parallel, then their slopes are equal. So if these lines are parallel, their slopes should be equal. So let's determine the slopes of each of these lines. So for line number 1, I have 2 points. I've got negative 1, 5, and I've got 2, negative 4. And of course, the definition of slope is rise over run, or the difference of my y's over the difference of my x's. So if I just plug in my values here for y2 and y1 and x2 and x1, I get negative 4 minus 5 over 2 minus negative 1. And negative 4 minus 5 is, of course, negative 9. And negative 2 minus negative 1 is negative 2 plus 1, so that's 3. And a negative over a positive is a negative, and 9 over 3 is 3. So my slope is negative 3. I rise negative 3 for every time I run 1. So now if we find the slope of line number 2, and it's also negative 3, then we'll know they have the same slope, and therefore they're parallel lines. If it's anything other than negative 3, no matter how close it is, the answer is nope, they're not parallel. If I keep going those lines forever and ever, eventually they will touch. So to find the slope for line number 2, once again, I've got 2 points. In this case, I've got negative 3, 3. And I've got the other point that I know is negative 1, negative 4. So I put those into my equation of rise over run, the difference of my y's over the difference of my x's. I get negative 4 minus 3 over negative 1 minus negative 3. So that would be negative 7 over 2. So the lines are close to having the same slope, negative 3 and negative 3.5, but they're not the same. So when I compare them, I see that negative 3 is not equal to negative 7 halves. Therefore, line number 1 is not parallel to line number 2. They are not parallel because their slopes are not equal, which is a requirement for parallel lines. All right. Our final objective is to use the slopes of perpendicular lines to help us solve problems. So let's do that with problem number 3 and problem number 4 in our notes. Problem number 3 is very similar to the one we just did, except we're not going to determine if the two lines have equal slopes to see if they're parallel. We're going to see if they have opposite reciprocal slopes to see if they're perpendicular. So to find the slope of line 1, I've got 2 points. I've got negative 4, 2, and I've got 0, negative 4. When I put those into my equation of rise over run, my difference of my y's over my difference of my x's, I get that reduces down to negative 3 over 2. For every 3 I go down, I go over 2, or you could think of it for every negative 3 I go up, I go over 2, rise over run. To find the slope of number 2, once again, to find the slope of line number 2, once again, I have 2 points. In this case, I've got 4, 3, and I also have negative 5, negative 3. So when I put them into my equation of rise over run, y2 minus y1 over x2 minus x1, I get that the slope of line 2 is 2/3. So hopefully now you can just look at these and tell that one's a positive, 2/3, one's a negative, negative 3/2, so they're opposites, and they're also reciprocals, 3/2 and 2/3. 3 is the numerator and the denominator in one, and 2 is the numerator and denominator in the other. So they are opposite reciprocals, but if I wasn't sure, I could always just multiply them, and when I multiply them, I get negative 1 to prove that indeed they are opposite reciprocals. And if they're opposite reciprocals, then the lines, therefore, are perpendicular. And you could just look at that and see that they sure look perpendicular, but the trouble is problem number 2 sure looked like they were parallel and they weren't. So you can't just look at them and see. So for example, problem number 4, we've got 2 lines. We've got this blue line, line number 1, which has 2 points, negative 5, 2, and 0, 0. And so its slope, when I put them into our equation of rise over run, the difference of my y's over the difference of my x's, I get that it's negative 2/5. And then when I look at slope of line number 2, once again, I've got 2 points, 0, 2, and negative 1, 0. And when I put them into my rise over run, difference of my y's over difference of my x's equation, I get that the answer is negative 2 over negative 1, which is just equal to 2. And so hopefully you can tell that they're opposites. One is negative, one is positive, but they are not opposite reciprocals. The line number 2 would have to be 5 over 2, not 2, which is of course just 4 over 2. The other way to tell is if I multiply them, you'll see that I don't get negative 1. I get close. Negative 4/5 is close to negative 1, but no, they are not negative 1, so they are not opposite reciprocals. And if they're not opposite reciprocals, then the lines are not perpendicular. And again, just glancing at that or looking at it, it's tough to see that the red line and the blue line are not perpendicular lines. All right, problem number 5 is asking us, what is an equation of the line that is parallel to y equals negative 3x minus 5 that contains the point negative 1, 8? Okay, so the first thing I need to do is determine the slope of the parallel line. And I have y equals negative 3x minus 5, and that's in the format of my slope-intercept form, y equals mx plus b, where m is my slope, and in this case, m is negative 3. So the slope of the line that's parallel is going to be negative 3. So now I determine the slope of the actual line I'm trying to write, and if two lines are parallel, then their slopes are equal, so the slope of the new line must also be negative 3. If the first line is negative 3, the second one must be negative 3 as well. Now the third step is to determine the equation of the line. And I've got a slope of negative 3 and a point negative 1, 8. And so if I have a point and I have a slope, I can use my point-slope form, which is y minus y1 equals m times x minus x1. So the slope is negative 3 is going to go there, and my negative 1 is going to go here, and my 8 is going to go here. So when I plug those in, I get y minus 8 equals negative 3 times x minus negative 1. And of course, we don't want to say a minus negative. We'll turn that into a positive. So there's my slope of negative 3, and there's my point negative 1, and there's my point 8. And when I take that minus negative 1 and turn it into a positive, my final answer is y minus 8 equals negative 3x times x plus 1. So there is an equation of the line that's parallel to that line, has the same slope, and contains the point negative 1, 8. All right, let's take a look at problem number 6, which is similar, except it's asking us to write an equation of a line that's perpendicular to a line and contains a point. But once again, the first step is determine the slope of the perpendicular line. We have y equals 1/5 x plus 2, which is in the format of y equals mx plus b. And so in this case, m is going to be equal to 1/5. Now we determine the slope of the line we're actually looking at. And if two lines are perpendicular, then their slopes are opposite reciprocals. So if my first line is my first line is 1/5, then the slope of my second line is the reciprocal of that, 5/1, and its opposite. If the first one's positive, then this one will be negative. So the slope of my new line is negative 5. So, because again, you can see that 1/5 and negative 5 are opposite reciprocals. Because if I multiply them together, I get negative 1. So now that I have the slope of the line and a point, I have the point of 15, negative 4, and I calculated the slope is negative 5. If I've got the point and the slope, I can use the point-slope form. So y minus y1 equals m times x minus x1, where my m is going to be negative 5, my y is going to be, my x is going to be 15, and my y is going to be negative 4. So y minus negative 4 equals negative 5, x minus 15. Here you can see that my slope is negative 5, my x point is 15, and my y point is negative 4. However, I got to change that y minus negative 4. A minus and negative turns into a positive. So we have y plus 4 equals negative 5 times x minus 15. All right, our final problem is a word problem about baseball. And it takes a baseball diamond, or the infield at least, and it puts it on a coordinate grid with the home plate at the origin, so that means 0, 0. And it tells us that a batter hits a ground ball along the line shown, and there's a player, looks like the second baseman, is at the point 110.70, and he runs along a path perpendicular to the path of the baseball. So what is the equation of the line on which that player runs? And these are the kinds of geometry that you do whenever you're playing sports. You just quickly figure out what's the fastest path to the ball, which is the perpendicular line, for example. Okay, so there's the line that he hits right there. That's the line that he hits. And there's the player that's going to move at a perpendicular line to try to pick up the ground ball, going there to a perpendicular line. Okay, so to do that, we know that it's a right angle, that's a perpendicular line. And so the first thing we have to do is to find the path of the ball. And so to do that, we have a point 0, 0, and we also a point right there at 60, 20. So we have 0, 0, and we have 60, 20. So we can use that to find our slope, and our slope is 20 over 60, or 1/3. We rise 1 for every 3 we run. So now we have to find the slope of the path. We have to find the slope of the line that's parallel to that ball. And so to do that, we know that the slope is going to be the opposite reciprocal of 1/3, which would be -3 over 1, or just -3. Because -1/3 and -3 are opposite reciprocals. If I multiply them together, I get -1. So now finally, 3, I have to determine the equation of the line that the second baseman is going to take from where he's standing now to the point where he's going to intersect the ball. And to do that, I've got a point where he is standing right now at 110.70, and I've got a slope of -3. So if I've got a point and a slope, I can use the point-slope form, which is y minus y1 equals m times x minus x1. My slope is -3, my x point is 110, my y point is 70. So when I plug those values in, I get y minus 70 equals -3 times x minus 110, and I can double check to show that my slope is indeed -3, my x coordinate is indeed 110, and my y coordinate is indeed 70.